Well, there is no sound.
Manchanda, I think they have not started.
Oh, thank you, Acharya.
Yeah.
No sound is fine. No sound, no audio is heard.
Can they hear us? Maybe they don't know that we are not hearing.
Yeah, we are not. I am not getting to hear.
There is no sound from the stage. Actually, I can hear the other people talking, but not from the stage.
I can hear you, but not from the hall. Same.
Not from the speaker. Yeah, speaker, there is no sound.
Yeah.
Okay, so typically PMTs are used as yes, check. Am I audible? Am I audible?
Now we can hear. Now we can hear.
Okay. So typically PMTs are used as photosensors in this camera, but recently silicon photomultipliers have emerged as alternative. And pulses from these PMTs and pulses from these PMTs or SiPMs are given to processing electronics. Now this Cherenkov light is quite faint and it lasts just for a few nanoseconds. So we need detectors with fast response as well as high gain. And also we need fast processing electronics. So PMTs and silicon photomultipliers basically satisfy this criteria. Now I mentioned that Cherenkov light is quite faint. So these observations can be carried out only from remote locations, away from man-made light, and also only during dark part of the night when moon is not there in the sky. So observation duty cycle is quite limited.
Yeah, now
No, there was one in between.
no, you can go back.
Okay. Okay. So this figure basically shows principle of IACD, that is imaging atmospheric Cherenkov telescope. So this is air shower generated by instant gamma ray, and then light from various Cherenkov light from various regions of this air shower is focused into the different pixels in the camera in the focal plane. So we get image of Cherenkov light from air showers. And by analyzing this image, one can get estimate of primary gamma ray energy as well as its arrival direction. Now, as I mentioned, PMTs are used in this camera, but now slowly SiPMs are replacing PMTs. Now, SiPMs are basically reverse bias PN junctions, and they are operated in breakdown mode. So, bias voltage applied is few volts above the breakdown voltage, and whenever optical photon is incident, it generates avalanche, and then that's how it gives rise to pulse. No, SiPMs have several features. Like they have much higher photon detection efficiency, as you can see in this figure. So as you can see in the bottom figure, SiPMs have higher photon detection efficiency compared to PMTs. Also, they need much lower bias voltage in the range of 30 to 70 volt, depending on the main. Whereas in the case of PMT, we need bias voltage of about kilovolt. There is another important advantage about SiPMs is that we can operate them in bright environments safely. This is not possible in the case of PMTs. So it is possible to conduct observations partially during moonlit and twilight part of the night. So that's how observation duty cycle increases when we use SiPM based camera. But of course, there are some drawbacks also with SiPMs, like they have crosstalk and their gain depends on temperature, and this needs to be compensated. Now, the camera that we are developing will be installed in the vertex element of tactic, which is operated by BRC at Mount Abu. So, this is basically tactic is basically array of 4 telescopes. Corner telescopes are called vertex elements, and center one is imaging element, that is PMT based camera. The camera which we have developed will be installed on one of the vertex elements. Now, after completion of tests at Mount Abu, we will shift this telescope to Hanle in Ladakh. This is the place where we are operating Hagar telescope array, and this is high altitude place. Its altitude is about 4.3 kilometers. Now, advantage of high altitude place is like that we can detect gamma rays with lower energies compared to what we can detect on mountains. Now, this camera has 256 pixels. Its physical size is 36 centimeter by 36 centimeter. It covers field of view of 5 degree by 5 degree. Size of each pixel is 0.3 degree. Each pixel is basically this 4x4 SiPM array. Okay, this pixel is basically 4x4 SiPM, also SiPM array. and light concentrator mounted in front. I think Shobha will give some details about this SiPM array. And it has breakdown voltage of about 50 volt and it changes with temperature. Now we have decided design criteria for camera electronics and mechanical structure, taking some inputs from simulations and also considering the geometry of this telescope structure. So this camera should cover dynamic range up to 1500 photoelectrons, and at the same time it should have single photoelectron resolution for low amplitude pulses. This is for the purpose of gain calibration. Then pulse profile should be recorded in 1 nanosecond waves, and observations will be carried out on dark nights as well as under twilight and moonlit part of the night when night sky background is quite high. Now, event rate is expected to be in the range of 20 to 30 Hz for dark night, and on bright part of the night it could be higher. So electronics should be able to handle event rate up to 100 Hz. Now, this entire electronics will be mounted behind SiPM pixels. So there is restriction on the weight of the entire camera assembly. It should be within 100 kg. Now, this is the schematic representation of camera electronics. So there is front-end electronics, which is basically where SiPM pulses are amplified and shaped. And then there is back-end electronics, where these pulses are digitized, trigger is generated, and data is stored. So today, Shobha will talk about front-end electronics. Next week, Sandeep Chauhan will talk about back-end electronics. And sometimes later we will have third talk. That is after collecting some data at one-to-one. DB Singh will talk about test results. So over to Shobha.
I'm privileged to talk about our imaging camera work by our team. I also want to thank Satya for giving me this privilege and Varsha for introducing our work. Varsha has already described about our camera, parts of the camera, but I'll be presenting details of this front-end electronics. So here, what you see here is our front-end electronics, this part, and what is pulled out is not. This is just for visualization. We have pulled out this one. So our front-end electronics is grouped into 16 identical processing modules, which we call as cluster cluster module. From now on, I call it as PCM. And in front of this, the front portion of the front. Okay. The front portion of this front-end electronics has our sensors, SiPMs, and attached to that sensor is the light concentrator for collecting the light efficiently, covering the dead spaces, and also to concentrate the light onto the sensor. Now I'll be talking about this front-end electronics block, which I call it as a pixel cluster module, PCM. And here what you see is the light concentrator, but you can see 4 here, but it's actually array of 4 by 4 array of light concentrator. We have divided our entire 256 pixel is what we have been using in the camera. We have divided the electronics to cater 16 pixels. And this is our, sorry, I'm very sorry. This is a new point. Okay, this is the sensor board, and here we have 16 pixel sensors mounted on this. And behind attached to the sensor board is the preamplifier, which is the one which actually processes the current signals of the sensor and provides the output. And here is the biasing system. The sensor has to be biased, and we have a certain bit complex biasing and essay what we call biasing system, which I'll talk in detail, and then the low voltage power supply for the cars. And these current signals from the preamplifier, the outputs from the preamplifier, which is in voltage, will go to the back end, and the entire
Different point there.
Okay.
No, this is good one for online. No one is to get it. It's coming down. Thanks, Anish.
Which is the point back end.
This is forward. This is forward.
I think I should get it. We have a complex biasing system which has to be programmable biasing is necessary. That is controlled by Raspberry Pi at the camera. And this Raspberry Pi talks to the remote control PC at the main control. And I'll talk this into detail. And what you see here is 16 sensor outputs going to the back end. Now I'll describe about the sensor board in detail. And this is the front face of the camera, which houses 256 pixels. And we have grouped 16 pixels into one processing module. This is the sensor board, which has 16, where this 16 sensors will be plugged onto it, and each connector is very ultra fine pitch microblade connectors here. And here this sensor board are the connectors for plugging in the preamplifiers. And what we call it as a sensor is in turn array of 16 SiPMs in 4x4 array. And each SiPM is again has 3,584 microcells. So this is what detects the light. What we call it is a one photoelectron or something. Now I'll talk about this bias supply. These SiPM gates have dependency on temperature. That is one of the drawbacks compared to the PMP. So we need to have an individual, all 256 pixels have to have an independent programmable bias supply. So why? One thing is this point I've already mentioned, and second is indirectly the gain varies with the intensity of background. This is because of the way we have biased the SiPMs. And the second point is we need, there are 256 pixels, and each pixel sensor can have a different gains. And our need is to have a uniform gain in the camera. And then this is whether you operate at Mount Abu or Henry, the temperature, there is a temperature variation. So during the observation night, we have some 6 degree to 10 degree variation. But we have, our goal is to maintain the gain of the SiPM uniform as well as same during the observation night. So this is a requirement. And the SiPMs have to be operated at the reverse bias and above the reverse bias. So we need the breakdown voltage of SiPM is something around 53, as you have seen in the previous slides, and the over voltage what we have chosen for our operation. This is after various study that we have done before we actually built our circuits. So the range that we require is 45 to 61, and then during our observation night, depending upon the sky condition, the current requirement of SiPM can vary from few microamps to milliamps. So when I say indirectly, what happens when the SiPM gain varies, the bias that we are supplying on it drops due to the series resistor. So this is one of the requirement that we need. To maintain, in spite of varying current, the load has to be, the SiPM current has to be, will change, but the gain we have to maintain. And another feature is, there could be sometimes, see we have 256 pixels, but in the field of view, there could be a small bright star or something coming, and one of the pixel, it may fall on one of the pixel, and the current at the pixel could be beyond our control, and we may have to switch off those pixels. So, and this on-off facility is very much necessary, and this is for temperature and load compensation during testing, as well as not in the during operation, but during testing, we need to have this kind of enable disable facility. And of course, every biasing system or every system need to monitor IV and T. Okay, now since we need an independently programmed biasing supply for every pixel, we cannot have and the gains of the SiPMs are different. We cannot have a single power supply and give power to all the pixels. So we have thought about this. We have come up this DC. Sorry. DC. Why am I? Okay. So, so DC-DC converters we have used, and this is the commercial converter which the range can be changed from 10 volts to 80 volts. SiPM, depending upon the make, their bias requirements can be ranging from 34 volts to some earlier ones were they were needing 80 volts, and this is the current capacity that each DC-DC converter can give us, and this voltage can be set through this control voltage from 0 to 25, and of course this will have overcurrent shutdown and voltage and current monitoring facility. We have developed in-house DC-DC converter parallelly while we were working on this, but a lot more work had to be needed on towards this, because at present it can give only 2.5 milliamps. When we operate when we operate at moonlight condition, the current what we need for SiPM can be more than 2.5 milliamps. But the pin compatibility and the form factor is same as the HV80. This will be taken up in future. Now we have 16 sensors in one PCM. So we have split that into 2 bias cards, and each bias card handles 8 channels. And using a microcontroller, Atmel microcontroller here, we are able to control and monitoring the bias supply. And the bias can be varied in steps of 5 millivolt, low noise, and on-off facility. And as I told you, we have to continuously monitor the temperature and we have to adjust the temperature. So we have adopted closed loop temperature compensation. And to read the sensors, sorry, I have to go back to that earlier slide, which I forgot to mention. We have two temperature sensor here. This one bias card will read this sensor. The second one will read this sensor. So to read this sensor, we are using a one-wire protocol. I think many of you may be familiar, but it is a single wire protocol. It has just one single wire for data and for reading to send data both ways. But it is cheaper also. So we have adapted that and it can be daisy changed to many devices. So, and also this one wire protocol, we need in situ calibration, which I'll talk about it later. At the preamplifier, we need this one address of the switch has to be operated. We are using one wire protocol for that also. And we have adopted customized serial peripheral interface to control all the bias board by single master Raspberry Pi. And when I say customized, normally this SPI comes with 4 to 5, and depending upon the variants are there in that. And every for this Raspberry Pi, these are the slave board. For every slave board, there are slave lines. So in our case, in the entire camera, we may need 32 slave lines, which will increase the lines. So what we have done is we have customized our device in such a way that using a daisy chain concept and then reducing the slave lines to just additional 2 lines called board select and board select clock, we have achieved this entire control of bias card. And the remote operation from the main control PC is through Ethernet. And this is just a block diagram of the bias supply. There is a microcontroller, and these are all the HV80s, 256 HV80s is controlled, and it is programmed. The control voltage is through the DAC, and for monitoring the current and voltage is again there is an ADC and one wire protocol reading the sensor and using the CSPI communication through the Raspberry Pi. And this is the entire bias system. What I'm showing, this is one board is here, but there will be 32 board daisy chains here, controlled by one single Raspberry Pi. Okay, now as I told you that this kind of complex bias system, we are able to achieve this was done. We kept this bias board as well as SiPM board in the environment chamber, and then we varied the temperature and we studied the gain variation of the SiPM pulses. When the temperature compensation is applied, then we could bring down the variation to less than 2%. If there was no compensation, it was around varied beyond 30%.
So, Shobha,
Yes.
Can you say from the experiment, what is the requirement? Within what kind of percentage, or you need to maintain the gain uniformly?
Okay, actually, as I mentioned, that each SiPM, each sensor, our sensor itself has 16 SiPMs. Okay, and we are giving single bias supply for them. And there are little variation among them also. And also this temperature, but we are maintaining the say less than 1% now.
So background noise, because the noise will also go up as a function of the how do you- So
Yeah.
how do you basically control the noise or reduce the noise? Do you take some measures for that?
See, we are operating at uniform gain. We are always maintaining the over voltage to be around 3 volts. Okay, you are right when the what happens at the when the current goes, the noise also increases. And this is the specs that is achieved by the bias system, which I have already described, and the temperature resolution at what we are reading is this, and the wattage of this card is this much. And there is a detailed, okay, more details can be seen on by this paper by my colleague Sandeep Kumar. Now, I'm sorry, I'll go back. Now I'll be describing this section, which actually the physics event, which is the one amplifying, which is the one processing the physics event. Okay. As Dr. Varsha Chekris has mentioned, there are certain design requirement and challenges in developing this camera. So one of the design requirement is we should be able to measure single photoelectron levels better, and that demands at least the signal to noise ratio should be greater than 4, and we need a wide dynamic range to 1 to 1500 photoelectrons. And for this gain measurements, once again I want to tell, our pixel sensor has 16 SiPM inside it. Okay, so to get a better gain calibration, we need to see the output of 1 SiPM from the pixel sensor. So we have to switch off the amplification for rest of the SiPMs. So we need this facility of in situ calibration to have a better do the better gain measurement. And of course, electronic noise should be less, and we should be able to process few nanosecond rise time pulses. And the challenges for the pixel sensor being 16 SiPM. So I think I have to go back. Sorry. Okay. Now this is the sensor board. Okay, and we have amplifier here. Then what happens is within this. We have only 15 mm for each pixel. Amplification has to be done within the 15 mm board dimension, but we have to cater to 16 amplification channels because every SiPM in the pixel sensor has 16 SiPM, so 16 anodes we had to be amplified. Anode current had to be amplified. So this will increase the large component density as well as the power consumption and the length of the PCB, electronics noise, and all the 16 SiPM has to be added analogly. Analog summing has to be done to get 1 pixel output. So this will increase the channel density. And the other design challenge was SiPM has a terminal capacitance of 320 picofarad, and it has a long tail. Sorry, I took up this one. It has a long tail of 80 nanoseconds. So what happens while processing, we'll be as such, our experiment is run with. Even though we have a very good pointing, we'll be pointing at the source, but there is lot of night sky background. So these backgrounds also get integrated along with the actual pulse we are looking at, and we'll also be integrating the electronics noise, and this NST, if it is high, there will be pile up and it causes a DC offset in our signal. And SiPM, the intrinsic, there is a capacitance at the detector, the terminal capacitance of 320 here, you might have seen in the earlier slide. This demands low input impedance amplifier because there will be a non-linear behavior, because the impedance itself keeps varying with the how many micros are fired. It has, every SiPM has 3,585 microcells, and depending upon the light incident on it, the output impedance keeps varying. Then there will be, we will lose on the bandwidth. So conventional charge amplifier and voltage amplifier cannot be used. So this is the preamplifier. This is one of 4 preamplifier what I am showing, and it has 4 channels. But each channels.
So conventional charge amplifier you can't do just because of long tail, or
No, because the output impedance keep changing.
okay.
SiPM output impedance keep changing.
No, the terminal capacitance changes.
Yes,
So
yeah.
No, but if you have charge amplifier, then the reservoir capacitance is much larger, right? So the individual pixel.
No, we actually we lose on the bandwidth when we use the charge amplifier.
Okay.
Another important reason,
He is
charge amplifier, here I required dynamic range is quite.
dynamic is also more of
Yeah, those must be ready.
Yeah.
Not,
So-
not due to terminal.
Not good.
So here there are we have to accommodate 16. I said no, each channel had to accommodate the 16 amplifiers. But to bring down the count of the electronics and the power as well as the cost, what we have done is before it is sent to the preamplifier, we have shorted the anode of the SiPM. We tried shorting all the 16, but then the capacity keep it will increase, and also the noise also. When we do that, the dark noise also increases along with that. So we thought by just shorting we could bring down the component density, power, etc. Everything, cost, everything by half. So this is the amplifier, and this amplified output will be sent to the backend electronics for distillation. And this is just this has been this is the pulse profile of SiPM when no light is it is not exposed to the light. What you see is the darkness itself, and it should the better the SiPM, you have to see only one peak. These are due to the noise, the dark noise. And when we say when we measure the gain of the SiPM, we take the difference between the successive peak. So there will be a distinct peak of how many photoelectrons have come.
I think we had here. We had this question about the dependence of dark noise on the temperature. That was the time when you were talking about noise. Temperature variations. You were also asking how do you control.
Yeah.
I think that was.
Yeah. Yeah.
A dark noise, dark cloud double or every 5 to 6 degrees Celsius.
Yeah, but we are only addressing the gain and hitting, but we have no control on this.
Exactly. You
We
don't
have
have
no
any.
control.
For example, max polarization camera, they say that temperature doesn't cross beyond 35.
Externally,
There
you
is
can-
active bullet is there.
So this is the arrangement what we have done. What you see here is 1 pixel. And when I say 1 pixel, it has 16 SiPMs. And 2 neighboring SiPMs anode are shorted. And this is how the biasing is done. And this is a typical, SiPM pulse, which has a long tail. And because of this, to overcome this problem with the long tail, we have shaped the pulse by using pole zero cancellation to something. The more you bring down, the more signal to noise ratio increases. So we have achieved around 20 nanosecond because our lifetime itself is around 8 nanosecond here.
Even changing the polarity.
Polarity is changed because there is an inverter inversion in that buffer. Non-inverting. See, because when you I'll show you. So when you sum here, it is always better to sum in inverting mode, not in non-inverting mode. Okay, because in inverting mode of the op-amp, it's what we call I forgot the term now, but it's actually the summing point is something like a ground. It's a 0 point. Okay, there is no linkage to the other section. So that's why we have to use non-inversion here. So that's why this pulse, okay. So these are the current pulses coming from the SiPM. We have a low input impedance trans impedance amplifier, and here we are shaping. This buffer is to match the impedance, and we are summing all the 8 subpixel pair current pulses into preamplifier output. And to get the dynamic range, we have a parallel amplification. Right now, this parallel amplification we push to the back end, because otherwise, instead of 250, we have dispenser for both the amplifiers, low gain and high gain. Otherwise, what happens, instead of 256, we have 512 cables running to the back end. So this was pushed to the back end electronics, and the subpixel on and off for the gain measurement, what I say in situ calibration, we are using this 1-wire control from bias card, and we can switch off this current from rest of the subpixel and just process this. And these are the salient feature of the amplifier, which is published in a paper. I think I'll move to the next one. And okay, now the performance test of the entire one module of the front end was done, and we have a good what you call the light box arrangement thanks to my colleague Bharat. Here is the laser based flasher system. We have pulsed laser, which is sub-nanosecond laser. And in front of the laser, there is a neutral density filter that is to control the intensity of the light coming out, and which comes through this aperture. And there is also a diffuser, because you need all the pixel has to be uniformly lit. So there is a diffuser, and this is our one of the front-end module is placed here, and there is white LED. I'll talk about that while. Okay.
So here, the distance between the diffuser and your unit and the fact that,
Yeah.
so how did you arrive?
All the measurement Bharat has done, he will be talking about these things in his next chart. He has seen that there should not be variation. Yeah, there should be some uniform light on every pixel. So sorry. This is that how we have to maintain linear range on the dynamics. This is for HG and this is for LG, and here up to 80 photoelectrons, and from LG 40 to 1500 photoelectrons, and we have maintained this overlap between these two for cross calibration.
So why it suddenly become flat?
Okay,
in case of any nonlinearity, it should be gradual.
No, because our electronics is not heat saturation. We will be often railroad saturation. It goes into saturation. Buffers and all that. So we have adjusted. Ajay, what you asked? Sorry.
Yeah,
Yeah,
you can see it's linear and then almost flat.
yeah.
But why suddenly that defines our dynamic range up to 1500 or something.
See, we have adjusted the gain.
It is saturated.
The amplifier gets saturated, the channel gets saturated. So we have adjusted and we have kept the overlap between low gain and high gain for cross calibration. Yeah, this will show the benefit of pulse shaping. Oh, I'm sorry. Okay. Benefit of the pulse shaping, what we have done. So what we did is we using that white LED there, we could emulate our night sky rays, and then so without shaping, what happened when the night sky background is on? In our case, that LED light is on. This is what the spectrum we get. So with shaping, we could see the distinct peaks here. And we could achieve, even though the signal to noise ratio is deteriorated, because with pulse shaping, there will be some attenuation. And this is the charge distribution of the SiPMs in the pixel sensor. We have 16 pixel sensor, but the amplifier channel is only 8. So what we have to do, because finally these are summed, and so we need to have a uniform charge in all the subpixels. So this variation, if you see, is less than 2% in our case. This is the technical specs achieved, and this has been published in this paper. And now all these amplifier, 4 amplifier cards and the 2 bias cards has to be powered, and this we are using the low voltage power supply board, which has we are using LDOs, which has very low noise, and the amplifiers are powered by these connectors, and the bias is just given to those bias boards. Okay, now I want to mention that, yes,
Previous slide,
yes.
what do you mean by saying minimum to ambient temperature?
Okay, these, okay, I'll tell you. Basically, these LDOs are designed, no, it's nothing to do with our car. Basically, these LDOs are designed.
You mean if the
Yeah.
temperature coefficients are
Yes,
somewhat good?
Yeah, control.
They don't need so much of
yeah,
cooling and
Yeah.
heating.
yeah. And all these boards fit into this, what we call it as a pixel cluster model, into this housing. What we have used is a plastic, ABS plastic 3D printed housing. And with this, the cost of this housing is low and it can be easily machined or fabricated, and we get the precise dimension because everything has to be fitted, tight fitted to form into a camera. And also this mounting screws has to be there inside this, but this cannot be done with if there is a metal frame. And you have to use a solid block and then scoop, and you have to give provision for the mounting holes. So, and all the connectors, orientation of the connectors and how they are going, the size of the PCB, everything is well thought of before the design, such a way that nothing comes out of this module, and everything is harnessed. There are enough gap maintained to pass these cables from the sensor board or from amplifier board to battery.
Well, you just mentioned briefly about the why you want to go for ABS, not metal and so on. But in some occasions, metal might offer a little better EMC.
Yes,
So,
yeah.
therefore, of course, it may be heavier, etc. But now,
Yeah. One of the reasons we have to.
Can I ask a simple question, Shobha?
Yes, yes.
Why didn't you adopt a ASIC-based imaging system rather than making your own amplifiers and so on? They are available now, 128 channels. The size is just like a nail.
ASIC, first of all, ASIC design was custom designed to particular, experiments, and they were very, very costly.
Costly?
Yeah, very
I'm
costly.
sorry. They are very cheap. In fact, they are dirt cheap nowadays. They are used in cameras. They were earlier developed for spark chambers.
Yeah, maybe our future cameras can adopt ASIC, but when we started, they were very costly, and they are customized design. So some of all the features may not be fitting on the design.
One more small quick question I want to know. What is the thickness of your detector silicon tube?
Sorry?
What is the thickness of the material, silicon, for your detector sensor?
thickness of the sensor, thickness of SiPM must be less than a half a millimeter.
But
No. How?
So sensor should be about a half a millimeter. Yeah, how do you use it? It is.
so can you
Sir, so what is your point, sir?
My question is, how do you get such a fast rise time? Is it just because you are limiting by your amplifier? If the thickness of the silicon is large, then you would not get that fast rise time at the output.
The SiPM typical rise times are a few nanoseconds. And
yeah, but that is because you are limiting the bias that way, no? Not that, that's why the noise will be increased. I also saw that your pole zero cancellation of the amplifier is poor. That is why you get a lot of fuss on the other end of your pulse. See, when you are doing very fast pulses, then after one pulse has gone through and the second pulse comes, the input transistor, input junction hasn't come to the base level. So you have to do what we used to call pole zero correction.
Yes, yes.
And that is an active way of bringing it to zero. Then you don't get fluctuation in the
Zero
output. So I saw that their correction is poor. And third, can you show me just that your temperature variation with the bias? Because there looks like rather too poor. Can you go back? I'm sorry, I am stopping you in between because for me it is at 10 o'clock, 9:45 in the night.
You
So,
were asking about this, this.
One behind, yeah, this one.
Okay, this is Sandeep, you want to tell something about this?
Now,
What is the question?
no, my question is that why can't you operate at 25 degrees it is equal? You can have a jacket which can temperature control rather than, because unless your all component are temperature compensated, especially the resistor which is going to the bias, and if the output is very sensitive to the bias, in that case the resistor change itself will affect it. So you have a jacket of a heater all around you about the sensor side. And that is what we used to do for laser. When we send laser up, we control the head because it varies the temperature. So you can actually heat the sensor part and fix it at 25 degrees. Within a 1 degree, you can control. And it's a ground-based system. You have no problem of the power there.
In case of our camera, all the silicon photomultipliers, they will be exposed to the atmospheric environment. So it will be operating in open environment, and controlling the temperature of silicon photomultipliers will not be possible there. So we are adopting an alternate solution where will be.
Wait a minute. What are you saying? If I wrap around a heater with a temperature controller and put the power in, why would not it cut off the power and control the temperature within 1 degree? We do it on ground, all the ovens. Why can't the head be controlled with temperature controlled at 25 sharp and you have no problem at all?
And this temperature vary in winter season, it goes up to -20, -25 degrees centigrade. So don't know how effective will be that individual.
Baba, it is not a surmountable problem. It will just take little more heat, that's all. Because your total capacity, heat capacity of the sensor is very small. You are not heating the rest of the box. Anyway, go ahead. I had this suggestion for you to think, so that because it is so difficult in an automatic way to control the temperature so precisely, because I see a large gain variation of factor of 2 happening at lower temperature.
It is 2%.
Is it 2%?
No.
70 to 150 is what? Is in millivolt, isn't it?
No, sir, I think this.
Shobha, keep the slide. Keep that slide.
Okay.
Sir,
This is without temperature compensation, and this is with compensation. This we have studied in environment chamber, but the latest studies have brought down to almost 1%.
So when you want a automatic compensation, that means your heating element temperature measurement has to be precise. And that, again, that's what I'm trying to say, that you will not be able to compensate so well, and your variation is much larger over a small change of temperature.
Okay.
That will affect your output.
Sir, we have to, she has to complete her slides. So maybe we'll get back after she is done giving the discussion.
Yeah. I just thought I will make suggestion because if my,
Sure.
my signal gets cut out.
Yeah,
Thank
thanks.
you, thank you. And this I want to explain, and this is the technique. Now I'm almost done. So these are, you can see, this is our PCMs, 4 PCM array. This is 4x4 PCM array is housed inside this camera housing. This is our entire camera. SiPMs are plugged on it. This is the front view. And the size of our camera is 70 centimeter by 74 centimeter by 90 centimeter. I'm almost done.
90 is a depth.
Height. Actually, 90 is the height.
90.
See, this camera will be facing, right? That is 70 by 74. Height, vertical height is 94. And the 74 is because, we have to house other things like power supply unit and then this interfacing plate between our camera to the telescope. So these are our team members, and here I would like to take few minutes to acknowledge special acknowledgement to our team members. Everything from the during our design stage, we have all 5 pitch components. Everything was done in-house by my colleague Ramdas Deshmukh, and very efficiently soldered. In fact, when the production PCB came, the sensor board, which has a grade, micro grade connectors, we faced every connector had a problem with the connectivity. But when it was done, our own person was doing better. We didn't have that kind of soldering facility. And the next person whom I have to acknowledge is, of course, everybody wanted to that, but all the hardware design was done by every board, every single board from front-end electronics, back-end electronics, but everything was doing parallel. Because that was 2 or 3 boards design was done parallel. So this is he needs to be mentioned. And of course, large density of component indent was very efficiently handled by Varshanika. Thank you. And of course, Chavan is always there from all the, since the development stage to the final camera. Very quick solution we had got from him. Thank you.
I think you have one question. You want to ask? Okay. First, let me first formally thank Shobha for this very nice work and all her teammates who really produced such a wonderful piece of, almost looks like a piece of art, and putting everything indigenously, trying make everything in house, and also of course ultimately meeting what the experimental needs are and so on. And I'm sure that they are going to on top of Zoom and going to, I think they already tested a sub-module of this some time ago, and they're going to now take a 256 pixel module to Montagu and test it, and all of us should wish her and all her team success for the field trials. So with that, let me take some questions from the audience. And also, if any of you on the Zoom or YouTube have other questions, including Professor Manchanda, please raise your hand or you unmute yourself and ask the question. Thank you.
My question is so much difference you have with one DCA module. So what is kind of model that is distributed in speed that is
Yeah, first is both the front end and the back end, the entire electronics takes less than 500 tons. Yes.
I have one suggestion.
Yeah.
From your unit, I see a lot of power and fans for cooling it. So you have enough heat being generated. So why not use mezzanine floor cold chamber? Just put it inside and switch it on and see how long, what temperature it maintains at say lower temperature when outside temperature goes to -10.
Yeah, this camera is supposed to be operated eventually at Mount Abu, but presently when we in the testing stage here, and that too we have to put this entire camera into the light tight box laser for testing. We need this kind of cooling system, sir, and also we don't know in Mount Abu what is the variation, because we'll be studying this once we go there.
No, but you can do it in chamber up to -40. Our chamber will take it downstairs.
So we have sorry. Okay, so thank you. That's I think my colleagues have to take this suggestion. They have a chamber that he says that this can be taken, this can go into the chamber.
Okay.
Thank you, sir.
Yeah, I think Srinivasan
mentioned about the particular capsule which you have made to 3D printing. What is so special about it? Why you need do it in 3D printing? Because does it look like an object shape or a complex shape? What is the reason for going
Because it's easily it's put in Nandikishore, you want to talk about that? Why 3D printing? Because it's fast. Because we wanted it quickly. The production happened very quickly.
It's an odd shape or odd size when it makes sense. Does it look? So, and
Also, that you are missing the point there. All those 7 PCBs are mounted there. Okay, there are these mounting arrangements that was there inside. It's not just a plain box. That's what I was saying.
What you mean say that after packing you made it everything together you made it or you made it?
No, inside. There are mounting holes and arrestments for the PCB.
not keep the PCB on that same housing.
Okay, thanks.
Okay.
Okay. Yes, Shobha. Can I take any other questions? Here one. Hey, can you give the mic to Prabhat?
Yeah, first of all, I would like to thank. So I would like to congratulate Shobha Varsha and her team for this successful project. All very nice project. I have just one question regarding this photoelectron department 4 to 1500.
Yeah.
So what is the scientific objective going to such high number of 1500?
This is based on simulations. Okay, we carried out simulations of gamma rays and cosmic rays over whatever like our energy range that we are going to target, and then we found that this is the optimum, like up to 1500 photoelectron.
You are the higher energy you are getting.
Yeah, higher energy falling near the telescope, we have highest photons.
Okay.
I don't see any raised hands. So are there any more questions? If not, we want to thank Shobha by giving away this nice memento of 40 years of asset colloquium. I hope you like it.
Very nice, because I'm retiring next month and I'll take this.
Right. So thanks all of you for your interactions. Please join for a cup of tea in the restaurant.
Yeah.
Thanks, Victor.
Can we kept here, no, sir?
I saw sometimes in your
No, you can take it later.
I can take it.
Otherwise, just take it. No, no.
I saw, but the entire this the frame.
There is a also, yeah, that text was partially open.
Partially.
But the light comes.